Hi, Andrew. Hi, Andrew.
Hi.
Sorry, just 2 seconds. Okay, can you hear us?
Yep. Can you hear me?
Yep, you hear me?
Tu sais comment on augmente le son, Christophe, pour, Ouais. Can you hear us now?
Yeah, I can hear you.
Great. Oh. Can you see the screen? Okay, perfect.
Okay, so hi everyone. I'm Xavier Tanier. I'm a professor here at Sorbonne University, and I'm happy to chair this committee. Maybe I can introduce you to the members of the committee. So Eric Gossier, professor at Sorbonne University, Sophie Rosset, researcher at Listen. Andrew Yates, online with assistant professor at IR Lab. Benjamin Pivovarsky and Stephen Clenchon, who are co-advisors of this thesis, and myself, Xavier. So the floor is yours.
Okay, great. Okay, so welcome. Thank you to be here. So today I'm going to talk about the work I did during my Ph.D., supervised by Benjamin Pivovarsky and Stephen Clenchon, and today we are going to talk about effective, efficient, and explainable neural information retrieval. So first, a little bit of context. What is information retrieval, or IR? So IR is the process in which users, so you and me, engage with a system to find answers that satisfy an information need. There are many types of retrieval systems, but search engines like Google, they are the ones we are the most familiar with. And so with such a system, we usually formulate text queries in the search bar, and we expect in return relevant documents that are ordered by their estimated relevance to the query. And so, for instance, we might look for the weather in Paris, or find a restaurant near the university, or if you have maybe a train to catch, check the date for the next strike. And so in this thesis, we are interested in what makes a text document relevant to a query. And so traditional approaches to IR, they rely on the hypothesis that relevant documents, they should contain query words. And actually, this is quite a reasonable assumption. So if we look, for instance, at this query from the Trek deep learning dataset, so here the user is looking for a person. So apparently it's an American sea captain. And we obviously expect relevant documents to contain this name, for instance, the corresponding Wikipedia page. And all the traditional term-based approaches in IR, they can be written as a sum over query terms of some weighting function. And for instance, we have the one of the most famous ones, which is the TF-IDF model, where we have two components. So the first one, the TF, with the TF, the score increases if the term appears more in the document. And with the second component, the score increases if the term is rare in the collection, so if it's more discriminating. And so we can wonder if keyword matching is enough, and if search is kind of a solved problem. Well, not exactly. I think we have all experienced bad search results, and there are many reasons for this. So for instance, we might, relevant documents, they might not contain query words. So for instance, if we consider this query still from the same dataset, we feel that there might be relevant documents that contain synonyms of the query words. And so this issue of the mismatch between the words in queries and documents is known as the vocabulary mismatch, and is maybe one of the most, the biggest issue that is faced by lexical approaches. But we have there are other reasons. So for instance, if we look at these two queries still from the same data set, we see here that we have the same word that appear in different contexts and has different meaning. And this type of issue is really hard to deal for lexical approaches. So lexical approaches, they are quite limited. It's not really a surprise. And early on, the IR community has worked on methods to improve the quality of search results. So for instance, many methods have been developed in order to fight the vocabulary mismatch, but in the end were not so effective. And early 2000, learning to rank models have been developed in order to combine many relevant features with machine learning models. But the thing is that developing such features is usually difficult. And so the rise of deep learning has given birth to neural information retrieval, where here we aim to have models that directly infer the relevance from the raw text data. But despite all the promises, results have been a bit limited. And one of the reasons is that most neural approaches, they relied somewhere or another on static word representations, like word2vec, which are quite limited. Which brings us around 2018, where we have witnessed kind of a turning point in NLP with the development of pre-trained language models like BERT. And so such approaches, they rely on the transformer architecture, and they are pre-trained on large amounts of text data, and they provide powerful contextualized word representations that you only need to fine-tune for your task. And we had kind of a breakthrough moment in information retrieval early 2019, when Nogara and Shaw completely shifted the state of the art on the MS Marco dataset using a simple adaptation of BERT for the re-ranking task. But while these results were impressive, there was still a limitation. So models like MonoBERT, but even like learning to rank or neural IR models, they are usually very costly, and they can only be applied to reorder a small set of documents that used to be selected by keyword-based approaches. And as such, they cannot really deal with the vocabulary mismatch problem. And so given the success of BERT in re-ranking, the community has started to wonder whether we could also apply pre-trained language models to the first stage ranking. And by doing this, we aim to have models, like semantic models, that can surface relevant documents that would have been missed by keyword-based approaches. And this way, I think we kind of fully uncover the potential of deep learning for information retrieval. And this offers interesting perspectives, but also some challenges, especially around efficiency, because IR has one specificity compared to most NLP tasks, is that models, to be useful, they need to be fast, because users, they don't want to wait for the results. And this problem is particularly concerning when we try to tackle the first stage ranking task, where here we want to retrieve from large collections of millions to billions of documents very quickly. And so all the first stage ranking models, they actually follow a representation-based approach, where we can encode queries and documents independently in the model, and relevant score can be computed with dot products, for instance. And so if we do this, then we can compute all the document representations offline that we can store in an index, and an inference time, we only need to encode the query and search the index. And so existing methods, they belong to two main families, namely dense and sparse. So with dense models, we are trying to learn dense, low-dimensional representations for queries and documents, and we can use approximate nearest neighbor search for the retrieval. And on the other side of the spectrum, we have sparse approaches that where we try to learn high-dimensional sparse representations for queries and documents, and such that we can use an inverted index for the retrieval. So when I started my PhD, the field was moving quite fast, but there were still some ongoing challenges. So for instance, why it's really interesting to improve the effectiveness of the model, we have to keep in mind efficiency aspect. And so this trade-off is central to this thesis. So the IR field kind of switched from traditional unsupervised lexical approaches to supervised ranking models. And so one natural question arises, how do these models generalize? And actually, this is quite important for such models, because as you can imagine, if you have a search engine, every day you have new queries, new websites, new domains, and so on. And so you need to have models that are robust to these changes. And finally, we are kind of witnessing the scaling laws, where larger models become more effective. We can think of the last GPTs, for instance, but their outputs are really hard to explain. But in the meantime, users, they tend to require more transparency and trustworthiness from the search companies. And so there is this tension that motivates the development of appropriate techniques in order to better understand the model we use, either from a structural or behavioral perspective. And so after this long introduction, I hope I have motivated you that search is exciting, moving fast, but also facing some challenges. And we have kind of shaped the two research questions that motivated the works in this thesis. So in the first place, we are interested in designing effective, efficient, but also interpretable by design and eventually robust IR models. But we are also interested in understanding how such models behave. And in particular, we want to verify whether they rely on well-established IR properties. And so the rest of this presentation is divided into three parts. So in the first contribution, we analyze the Colbert model. And then, motivated by our findings, we propose an original approach to the retrieval problem called Explainable, which is the main contribution of this thesis. And finally, we take a step back and we compare how different semantic models behave with respect to semantic matching. So let's first dive into our first contribution towards analyzing Colbert. So when I start building new models, and we are especially motivated by sparse approaches, but we kind of hit a brick wall. And so we decided to take a step back and try to understand better how a current model behave, especially in order to help us a bit. And especially because at that time, little was known about pre-trained language models in the context of information retrieval. And so we decided to focus on the Colbert model, and I will explain later why. But first, let me describe how the model works. So you feed your query and your documents to BERT independently, and then you compute an interaction matrix where you gather all the pairwise cosine similarities between contextualized term embeddings. So on the rows here, we have query tokens, and on the columns, we have the document tokens. And after, for each query token, we select the maximum value among document embeddings, like document token embeddings. And we do this for every row. And the final relevant score is simply a sum of these scores. And what is interesting with this model is that in the end, it kind of looks like a term-based model. And we can explicitly see which term of the document matches to a given query token. And so in the end, we can take advantage of this similarity to analyze the model from an IR perspective. And that's why we chose to focus on the Colbert in the first place. So we are going to show that Colbert implicitly relies on a notion of term importance and also on lexical matching, and the latter being due to a particular property of the embedding space. But first, let's focus on term importance. So if you remember what I said earlier in the introduction, for lexical models, there are words which contribute more to the final ordering of documents. And so, for instance, we can look at measures like IDF. But when we look at Colbert, things become a little bit more complicated because the weight for a query term depends on both query and document context. And so our idea is to look at the contribution of a term. So more specifically, if we consider a query and the original ranking that is given by the model, and now we consider the ordering that is given if we remove the contribution of a given term in the query, then we have two rankings. And our intuition is that if the rankings are very different, then the term is important from the model's point of view. And so to compare these two rankings, we are going to compute some correlation. So we use epic correlation, which is similar to Kendall-Stowe, but gives more importance to top position. And so if it's equal to 1, it means that basically the rankings were the same. And so the term is not really important from the model's point of view. And so we compute this measure for all terms in Trek 1920 queries. And we plot this against a standard measure of term importance, which is IDF. And so on the plot here, we bin the X values just for clarity. And what we observe is a slight negative correlation between the two measures, which tends to indicate that Colbert implicitly captures a notion of term importance. And so now we turn our attention to keyword matching. So when we look at how matching occurs in Colbert for a given document, there are two options here. So either the model is doing keyword matching, and so the max value is obtained for the exact same word in the document. So if we have the query average annual income here, the term in the document would be income. And on the other hand, the model can do a semantic matching where the max value is obtained for a different query word, so here salary. And by comparing the distribution between the exact and soft cases, we show in the paper that the model, despite its semantic nature, still rely on lexical matching for terms with high IDF. I don't have time to detail things here, so you have to trust me. And after having shown that, we try to understand the reason for this behavior because it doesn't seem so obvious. And our hypothesis is that some representations are actually less contextualized than others. And if that's the case, by construction of the Colbert scoring, the max selection will tend to always select this exact term in corresponding documents. And so to check this hypothesis, what we did is that for every term in the Trek queries, we collect an ensemble of contextualized representation on the MS Marco passages. And so for each term, we have a matrix, and we are going to decompose these matrices with SVD. And after that, we compute a measure of dispersion based on the singular values. And if this ratio is high, it means that the embeddings are not so contextualized in the end. And once again, we plot this measure against IDF. And what we observe is actually a high correlation between the two values, which means that for terms with high IDF, the embeddings they tend to be more static. And what is really interesting is that this property is reinforced if you fine-tune your model. Which means that when you train your Colbert model on relevance data, it learns to rely on lexical matching for important terms. And so to conclude this part, we have shown that Colbert implicitly relies on the notion of term importance and relies on lexical matching for important terms. And that's why actually we turn our attention back to sparse representations, because such models, they actually encode these properties more explicitly. But they were not so popular at that time and not really effective either, at least less effective. Which brings us this called SPLAID for sparse lexical and expansion. And we have several publications covering these models from the initial formulation to later improvements. So this part is organized according to our research questions. So I am first going to motivate the approach and present a first iteration of SPLAID that is both effective and efficient. And then I highlight how the representations are interpretable. And then I briefly mention some more efficient extension, and we focus a bit more on improving the effectiveness. And finally, I will also analyze the generalization capabilities of SPLAID. But let's talk about the model first. And to recontextualize things a bit, let's talk about a sparse model for information retrieval. So as I already said earlier, these models, they aim to learn high-dimensional sparse vectors for queries and documents, such that you can use an inverted index for retrieval. And we have kind of three families here. A first family that models expansion, but no term weighting. We also have some models that learn term weighting, but not expansion. Sorry. And the last one kind of allows you to do both by representing queries and documents as sparse vectors. And actually, the first approach doing this was before BERT. So the SNRM model learned latent topics with a neural network. But later on, different approaches have relied on BERT to do something that is similar. But instead of learning latent topics, here the idea is to represent things in the pre-trained language model vocabulary using the mass language modeling head. But why using the mass language modeling head in IR? If we take a step back and consider what BERT is doing at pre-training, so we have an input text and we are going to mask some words in the input. And the objective is to try to predict those words given the context by modeling a probability distribution over the vocabulary. And when you do this, you actually implicitly learn to perform expansion. So if we look at an example here, so we have a query from the robust datasets. We consider a distilled-BERT model. And so for each query term, we have the top three highest logits by the MLM head. And so, for instance, if we look at the word detection here, we see that indeed the word is predicted itself. And this is this is the reason of the MLM head. But we also see that close words like identification and screening have high logits. And because we know that expansion mechanisms in IR are useful to bridge the vocabulary gap, it kind of motivates to actually reuse this head for models. Sorry. And so now let's describe the model in details. So it was actually inspired by the Spartan model that was released a bit earlier, but we made some improvements to the model that made it much more effective in the end. So we feed a query or a document to BERT, and then we get the contextualized embeddings that we are going to map back to the vocabulary using the MLM head. And so what you get here is an unnormalized log probability distribution over the vocabulary for each input term. And so these logits, they can be seen as estimating some importance for each vocabulary term. And after that, we use some log saturation on term weights, which was actually inspired from traditional approaches to IR, but has also successfully been applied to neural architectures. And after that, we do some max pooling over the input tokens, and we get a final representation in the vocabulary space. And so when we do this, we allow the model to both learn a term expansion, but also a term weighting. And yes, so to get the score between a query and a document, we simply compute that product. So now that we have an architecture, let's train it. And so as everyone working in neural IR, we rely on the MS Marco dataset to train models. It contains around 500,000 training queries with corresponding relevant documents. And so we initially relied on standard training techniques. More specifically, we trained the model by minimizing the negative log likelihood of the positive passage against a set of negative passages that are sampled with BM25, but can also be sampled within the training batches. But if we do this, we are not efficient because we need, remember that we need the representations to be sparse if we want to use an inverted index. So we simply propose to use a sparse regularization on query and document representations. And this is actually what the SNL model proposed to do. But the problem with L1 is that you are not entirely sure to be aligned with the retrieval efficiency, which can be better approximated as the number of operations you need when you compute the dot product between a query and a document vector. And this is actually what the flops regularization is proposing to do. And so here you are going to make the representation both sparse, but also more spread in the vocabulary. And so with SPLAID, we have an hyperparameter that controls the sparsity, so the strength of the regularization, which means that we have a trade-off between effectiveness and efficiency, and both aspects were learned end-to-end. And so if we look at first results on MS Marco dataset, we see that the model is a state-of-the-art for sparse models and competitive with respect to dense bioencoders. But as I said earlier, we actually have a compromise between effectiveness and efficiency that is controlled by the lambda. And so we are going to show this trade-off here. So on the y-axis, we have the performance on the MS Marco dataset. And on the x-axis, we have the flops measure, which once again is some proxy of efficiency for SPLAID models. And so the higher, the less efficient. And we see that if we train different models with different lambdas, we have this trade-off. And just to give you an intuition here, if we take this model, 20 dimensions that are non-zero and documents around 150. And if we take a model that is more on the left, so with more constraints, then it's much more efficient because we have documents with around 30 non-zero dimensions out of the 30K vocabulary. But we lose a bit of effectiveness. And so we have seen that these representations, they contain just a handful of dimensions, but actually what do they contain? So if you remember with SPLAID, we represent queries and documents in the vocabulary space, which means that we can directly interpret the representations. So for instance, if we take this query from the Trek Deep Learning dataset, we see a bunch of effects here. So first, due to the regularization, some non-important terms in the input are actually removed from the final representation. We also see that every token in the output has a weight according to its estimated importance. But more importantly, we see the effect of expansion. So here, every word in black in the prediction are actually not in the input. And so we see, for instance, how the model predicts a synonym of query words that are kind of useful to bridge the vocabulary gap. And so on the document side, we see more or less the same thing, but models can do more compression usually. So we have seen that SPLAID is effective, efficient, and also interpretable, but there are actually a few issues with the efficiency. And so I just give a brief overview here because I'm a bit short in time. So in the thesis, we show that actually minimizing the flops regularization is not entirely aligned with the actual search time or the query latency. And this is partly due to the fact that standard implementations of inverted indexes, they are quite inefficient to deal with long queries, which is the case with SPLAID because we do a lot of query expansion. And so we propose some more efficient or aligned version of the models in order to partly fix this issue. And so now we are going to further improve the effectiveness of the model. Because so far our models have been trained in the simplest training setting, but actually new training strategies have been proposed to improve the effectiveness of dense bioencoders. And so here we have, So for instance, we have distillation, which has been used, in IR to distill effective but costly cross-encoders to more efficient architectures. And so we have approaches like margin MSE. Several approaches have proposed techniques to provide better negatives to train the model. So instead of BM25, the idea is to get more informative negatives. And finally, some works have hypothesized that MLM pre-training is not entirely aligned with the IR task. And so they introduce intermediate pre-training or middle training task to better align the model. And so we have a very simple research question. Can SPLAID benefit from the same training improvements? And so we just propose to train various SPLAID in these different settings. So if we go back to our effectiveness efficiency trade-off, so this is the plot I've shown you earlier. So here we have SPLAID. We see that if we train the model with margin MSE distillation, we have nice improvements in effectiveness. And so in all the subsequent settings, we use distillation by default. In the second setting, it's kind of a two-step process. We are going to use the previously trained model to sample negatives for another round of training. So here, once again, the idea is to provide samples that are more informative, more difficult, in order to help the training. And once again, we see some nice improvements in terms of effectiveness. In this new setting, it's more retrievers to mine the negatives. So the idea here is to have maybe a more diverse set of negatives. And we see slight improvements on the MS Marco dataset. And finally, we have two last settings where we are actually going to consider the two previous ones, but instead of initializing the model with distilled bursts, we are going to use a co-condenser checkpoint that is supposed to be better aligned to the IR task. And so once again, we see some nice improvements for both cases. So if we compare to sparse approaches, just in terms of effectiveness here, so we are not comparing efficiency, we see that we have state-of-the-art results on the MS Marco dataset. And so now if we compare to dense models, we see that we have results that are competitive with the state-of-the-art. We are still a bit under the Colbert V2 model, but it's a model that is a bit more costly. So we have shown that the model is effective in domain data. So when we evaluate on MS Marco on which the model has been trained. And so now we are going to focus on robustness and generalization aspects. So specifically, we are going to evaluate SPLADE on a zero-shot setting. And luckily, we have the beer benchmark to do that. So this benchmark consists in 18 retrieval datasets to evaluate IR models in zero-shot. So for instance, we have different domains, for instance, medical retrieval with track COVID, but also kind of different IR tasks, for instance, entity retrieval. And what they showed in the beer paper is that actually most neural models, they fail to outperform an unsupervised lexical approach when you go on out of domain. And so if we plot the same trade-off as earlier, but here we have the average performance on the beer datasets, we see that more or less the results from in-domain, so the training improvements, they apply to the out-of-domain setting. But more importantly, what happens when we compare to other approaches? At the time of publication, we got state-of-the-art results on the beer benchmark. And we were actually quite happy with these results because our original motivation to work on sparse models was that lexical matching was somehow important for models, especially when you go on, for instance, new entities and things like that. And so these results, they kind of aligned with our initial intuition. So to conclude this part, we have proposed a model that is effective, efficient, but also interpretable by design and robust. It has been tested in different search services at Naver, so it's also a good thing. But there was still a remaining question at this point because we wanted to understand a bit more why the model is that good in zero-shot settings. So it motivated us to get back on analysis again, which brings us to the third contribution of this thesis, where we are going to analyze the how neural ranking models behave with respect to keyword matching. So we know that neural models, they are good at semantic matching, but it's unclear whether they are still good at doing keyword matching. And we saw earlier that some models, they seem better at generalizing. And at that time, we wondered whether there could be a link between the two. So in this contribution, we are interested in the ability of different neural ranking models to perform lexical matching. And so we propose a measure to quantify that. But in a second time, and this is more interesting, we check whether this ability changes when you check this on terms that have not been seen at training time or when you go on, out of domain. So let's first focus on the measure. And we actually kind of follow a simple intuition. So if we want to check whether a model is doing lexical matching, we are going to check if query words appear in retrieved documents. So just to illustrate, imagine we have this query. We are going to count these query terms in top K documents for different systems. And we want to compare how things are different. But if we only look at frequency, it's not enough because we know that some terms are naturally more frequent. And additionally, there are some terms that are not really correlated with relevance. And so what we want, or what we need, is a measure, term level measure that takes into account both collection statistics, but also relevance annotation. And actually, we can use the Robertson-Spark-Jones weight, which quantifies to which extent a given query term allows to distinguish between relevant and non-relevant documents. And so to compute this, we need to estimate a bunch of probabilities. And once again, we estimate this from the collection statistics and the QRLs. And just notation-wise, we consider this to be the user point of view because it comes from relevance. And so now we can define a similar measure from the model's point of view. by assuming that top K documents that are retrieved by the system, they are relevant from the model's point of view. And in order to measure the lexical match ability, we are going to compute the difference between the system view and the user's view. And so if this quantity is positive, it tends to indicate that the model overestimates the importance of this term. So basically, it retrieves it too much. And if it's negative, it's the other way around. And so we plot this delta against the user's weight for all the terms in Trek 1920 queries. And once again, we bin the values on the x-axis for clarity. And so we consider different representation-based model. So we have dense by encoders, late interaction with Colbert, but also sparse with Splade. And we additionally have a lexical approach with BM25. And so if we look on the left bin, here we have terms with low RSJ, and these terms, they are not really discriminative. So we are not really interested in these terms, and we see that models more or less behave the same. But now, if we look on the right, here, these are terms that are supposed to be very discriminative for this query. So these are terms that the model should retrieve somehow. And we see that lexical models, they tend to overestimate a bit their importance, but that neural models, they tend to underestimate it a bit, which is kind of expected because they are semantic models, so they are supposed to do less keyword matching. But now we focus on something more interesting, which is the ability to perform lexical matching for terms that you haven't seen at training time. So here we add in the same plot the terms in Trek queries that appear in less than 10 training queries in MS Marco, so out of the 500K. So these are terms that are barely seen at training time. And we see that BM25 is roughly similar in its estimation, and it's expected because the model is unsupervised, so it should be rather insensitive to training statistics. But now when we check neural models, we see that they tend to underestimate even more the importance of these terms. And we additionally observe that there seems to be a kind of an order, a difference between models in their ability to retrieve exactly these important query terms. And so, for instance, we see that Splade seems a bit better at retrieving terms that are not seen at training time. And so we kind of hypothesize that this might be one of the reasons that could explain its good out-of-domain performance. We also show in the paper that the same applies in zero-shot. Zero-shot condition, but I don't have time to detail this part either. So to conclude this part, we showed that the ability to perform lexical matching is kind of architecture dependent, and that overall neural models, they fail to properly generalize term importance on out-of-domain collections or terms that are almost unseen at training time. And so it's now time to conclude. So in the course of this PhD, we have witnessed and to some extent contributed a bit to the paradigm shift in information retrieval. And so in terms of perspective, there are two axes that I want to discuss. So I have briefly mentioned when talking about Splade that we had some efficiency issues. And so actually we only scratched the surface during my PhD. And so, for instance, my colleague Carlos and my advisor Stefan, they proposed more efficient versions of Splade. But the thing is that when we use inverted indexes with traditional query processing algorithms, these techniques, they are actually designed for term-based approaches. In particular, they assume a certain distribution of term weights that is not observed for sparse representations. which questions maybe the adequacy of traditional retrieval algorithms for this new class of models. But more importantly, it also questions the very nature of the standard index and retrieve paradigm in IR, because usually it's really hard to optimize this pipeline in an end-to-end manner. And recently, some people have been working on a new class of neural IR models called generative retrieval, where everything is encoded in the model's parameters. And I think it kind of opens the path to a better optimization of these aspects. And finally, one other axis I want to mention is more generally sparse retrieval. So we have shown that SPLAID is effective for the ad hoc task, but we have also recently shown that it can be used in a conversational setting. And some people have extended the model to cross-lingual information retrieval and also cross-modal information retrieval, which I think questions the representation basis for this class of models, because at the moment, I think they are a bit too tied to the pre-trained language model vocabulary. And finally, I think retrieval is kind of a hot topic at the moment, and this goes beyond search engines. So large language models, they are increasingly equipped with retrieval models in order to provide a better context or references for the generation. And so I will be curious to see how we can apply SPLAID in such settings. So yeah, this is just a summary of my contributions, and thank you for your attention.
Thank you. Thank you. I'm giving the floor to Eric Bossier, who is one of the two reviewers of your work.
Thank you, David. Okay, so thank you very much for your presentation. Thank you also for your work. I think I said in my report that I was quite impressed by the work you did. What impressed me the most, I think, is that the proposal you have is quite simple conceptually, I would say, but very effective and efficient, as you mentioned. And this is very difficult to achieve that in general. It means that you master this field quite well, and in order to have something that is conceptually simple yet impressive in terms of the results and in terms of the impact it has on the community, it is not that easy. So that's okay, that I wanted to mention.
Thanks.
I was also impressed by the number of slides you had.
Yeah.
And I think you win the contest of having the largest number of slides in the presentation by a large margin. But okay, this is really important. Okay, so yes, I do have some questions.
Yes.
I mean, that's why I'm here also to ask you questions. So the first one is that you tend to sometimes talk about importance and discriminative terms. Sometimes there are synonyms in your presentation, sometimes not. And so in the first part, you're talking about important terms and measuring IDF, which is a measure of discrimination. So and then at the end, you're talking about you're using RSJ, and but you also say that they are discriminative. So maybe don't you think maybe we can try to differentiate them and to have okay. But my question is, what if you differentiate them? What are the conclusions that you draw from the part on IDF for discrimination and the part on RSJ for importance? Because otherwise I believe that slightly contradictory to the discourse that you know.
Okay. The first thing I want to mention is I think that the two measures are actually quite correlated.
They are correlated, yeah. So what is it means quite correlated?
Yeah, I mean, so I remember that I looked at the correlation between the two values. I think it's even in my manuscript.
Yes.
So I think there is a strong link between the two values. I think we could have done the same type of analysis that we did earlier with IDF with the RSJ.
Yeah.
I think that overall it just gives you a better estimation because you use relevance annotation. So I mean, I'm not so sure.
Wait, in RSJ, you take into account, okay, the document frequency is certainly taken into account in one way or another via the probability, which is not the fact in IDF at all. And so, for example, in the first part, where you more or less conclude that Colbert implicitly models IDF, well, it's not that. For me, it was the result was not that clear cut, and it's not that intuitive that Colbert integrates some kind of IDF in a way. And so, I mean, the fact that one relies on TF even implicitly, and the other one not at all. So they're not completely identical. They don't measure exactly the same thing.
No. But yeah, I think initially with Colbert, we wanted to check if like there were similarities between like if you take I don't know BM25, but just like TF-IDF more simply between this model and the way Colbert models importance.
Yes. Yes, TF-IDF I would have TF-IDF is closer to importance than I would say.
Yes, okay. Because but I think when you look at MS Marco passages, the TF is not
true. That's important, you mean?
Yes. So that's one simplification.
Yeah.
But for most terms, actually, the passages are really short. So usually the TF is equal close to 1. So IDF.
Yeah, but this is not true on other collections.
No.
Yeah.
No, on other collections.
And okay, so another question related to that is, don't you and have you thought of trying to enforce in your model the fact that TF-IDF or RSG, the fact that one can take into account this kind, for the model to take into account this kind of attributes in the representation?
You mean more explicitly?
Yes, more explicitly. Yes.
Yeah, I think at the beginning of my thesis, I've tried simple things. I mean, it was like different models, but for instance, like trying a dense bioencoder where you have some IDF weighting when you average the embeddings or things like that. I don't recall having seen some real improvements.
Yeah, no, I think it's not easy.
But there might be other ways. Yeah,
okay. Yes, I also had a question. I mentioned that in my report regarding the logarithm that you used on your weighting scheme, which was not that's was not obvious to me why this was working better, because okay, you mentioned that this is a sort of a saturation over the weight, and it's true that it's used to saturate the TF, for example. But I mean there are strong motivations for saturating the TF.
Yes.
That, okay, when you increase by 2 or by 10, it's not the same if it's 100 or 1. But in that case, it was not clear to me then why you gain, and you have a sentence or two in your which were not entirely clear to me. So I wanted to ask you.
So for instance, one thing we noticed initially, I did some experiments without this saturation.
Yes.
And then we tried a bunch of different things, and we saw that it worked better. When you, for instance, when you plot the effectiveness efficiency trade-off. And I think one argument is that when you have a saturation, if you want to, so imagine you have a query, a positive document and a negative document. If you want to increase the score of a positive document versus the negative, if you don't have any saturation, then you can arbitrarily increase some dimensions of the representation. And so on the other hand, if you have a log saturation, for instance, you have some bounds on each dimension. And so one way to actually increase the score of the positive document is to lower the score of the negative one by putting to zeros many dimensions. And that's why we saw that, for instance, if you train a splayed model without any regularization, with flag activation, it's already sparse by nature.
Yes, but you have this. You can have the same with the original measure. I mean, you can also say one way to gain is to put to zero the weights of the negative documents as well.
Yeah, but I think it's not the. I mean, it's not. Yeah, I just think that it's easier when you have the log, because I think the log, it really enforces some dimensions to go to zero, because at some point you cannot increase the, let's say, the relevant dimensions. So you need another way to discriminate between a positive and a negative. And one way to do that is to actually put to zeros for the other.
The log is usually not used for that. It's really used for saturation.
Yeah.
But okay. That I'm still a bit surprised, but okay, I do believe you. That's happening, of course.
I think that Stefan has tried other saturation functions that were inspired by like his previous work in IR, I think, with other concave log concave function. But in the end, it was. I don't think it was extremely conclusive. Yeah. So we stick to the log.
Okay, thank you. So another question I have. So there are 4 properties of your model: effectiveness, efficiency, interpretability, robustness.
Yes.
So the first 2 ones, they are very clear because you enforce them. So there is no questioning that it is by design. And then you say interpretable by design. I understand why you say that, but I will try to challenge it a little bit.
Okay.
But I don't say you're wrong in saying that. But you say that, if I'm not mistaken, because you rely on sparse representation. So you rely on a few words to match queries and documents so you can always go back to show to the users but then. Okay, the point I would like to make is that there is some kind of expansion in Splayed, because you mix the two builds in a way, and so you don't exactly control what's happening in this extension.
No.
And so that's why. Okay, you can still show. Okay, these are the words on which the matching was based, but then why were these extra words which are not in the query chosen? For example,
you don't have the clear explanation for it.
Yeah, I mean, you have this experiment, or you not experiment, but you have this illustration where you show, okay, they tend to be synonyms. Yeah, but my question was, have you tried to do a more systematic exploration using GoNet, for example, trying to see whether expansion terms are mostly synonyms or things like that, or because otherwise, I mean, you may not be able to really explain to the users what these terms were.
Yeah, we haven't explicitly worked too much on this interpretability thing. I think it was just, as I said, kind of byproduct, by design. It's a cool feature, but I agree that it's not. I mean, it's not entirely perfect. And for instance, so I think I have shown some nice examples, but for instance, it's not always the case. So sometimes expansion doesn't work, or it outputs words that you would not expect, even stop words and things like that. So there are sometimes behavior that are really strange, and that may be more difficult to explain. So I mean, there's still some work to do.
Okay. Well, almost the same question for robustness. This time, okay. So intuitively, you are in between the neural networks and let's say the lexical matching systems. The latter being more robust than the former. I mean, this is just an experimental result, right?
Yes.
And so you are in between them, and so you are in between them in terms of robustness, as you have shown us. But do you have any other intuitive explanation on why your model is robust?
Yes. So one that could be an explanation. Not so sure.
I'm not so sure either.
Yeah, is that what usually happens with Splade is that all the input terms that look important, and so I will carefully use importance now. They tend to appear in the final representation, and this happens even for terms that you haven't seen at training time. So this is just a property of the MLM head to kind of reproject terms to themselves, which means that even for terms that you haven't seen, you will tend to have those terms in the output. But because this happens in both query and documents, then you are almost sure to have some sort of lexical match between those terms.
Right.
So it's likely that the weights they are not really well calibrated, but still there is a match that is occurring.
Okay.
Which might be the reason, but at least one of the reasons.
No, that's a good point. In a sense, you're telling that the neural nets, they well, it's a bit contradictory, maybe what I'm going to say with what you showed on Colbert. That neural nets, they fail to have to rely enough on exact lexical matching.
Maybe yes.
Yeah. Okay.
But Colbert is a bit different because we usually put it in the dense case, but it's more in between lexical and dense because there is still like a term level matching.
Yes.
So for Colbert, I don't know, but for dense by encoders, I will tend to say that it's harder for them to do lexical.
Yeah. Okay. No, that's an interesting explanation. My last question is from the perspective where you mentioned generative IR.
Yes.
Can you tell me more about that?
About
what you plan to do with generative IR?
Well, I don't have any plans yet, but I just think it's I think it's an interesting like work direction. I haven't had the time to start working on new things because the last few months were a bit busy finishing the thesis, but I think, for instance, there is a workshop in CIR about generative retrieval, so more and more people are working on that. I think like initial experiments they were quite limited because I mean it's really difficult to make this model works and to scale and so on. But I think like the community is starting to tackle this issue a bit more. Yeah, I think it's really a nice perspective, but I don't have any plans yet.
Okay. Or you don't want to tell me that?
Maybe both.
Okay, we'll discuss. Thank you very much. Congratulations again.
Thanks.
Thank you. Sophie Rosset is the second reviewer of this work. Your turn.
Yeah. So first, I would like to congratulate you because your work is amazing. I really like it. The Splade model because it's very simple, very elegant, and it works well. It's not very frequent in a thesis to see that, so congratulations. I also have to say that I really like your presentation because it answers some of my questions.
Okay, great.
So it was very interesting to see that. I understand that it was not easy to go back from analysis and the model and so on, but it was very good. So thank you. I'm not an expert in information retrieval, and so I won't have a technical question, but and also Eric stole my questions. And, I had 3 or 4, but it's not very important. The first thing I have is that it's about a question that Eric had about interpretability, and you say that your model is interpretable by design. I think that you have 2 definitions, and I mean maybe interpretability is more about do we know what is used to do the retrieval, and the explainability, which is why and your model is not able to say why it has been used. Do you think you could do something about that? Because, yeah.
That's a good question. I haven't thought about that, so I don't know if I will have an answer for this. But yeah, I agree. It's an it's an interesting question. I think it kind of. This is also what you said, Eric. But yeah, sometimes you see some expansion terms. Okay, they are here. You don't really know why, and sometimes you have strange cases. But yeah, I'm not so sure I have an idea of how we could try to explain what are in these representations. I really, just thought about the interpretability from the okay, we have this representation, so we can see when we score a query in a document, what are the most important terms. But yeah, I agree that once again there is still some work to do on this side. Yeah.
Yeah, the question is more because you use sometimes interpretability, sometimes
maybe
and I think it's two different things.
Yeah.
Not the same, and the model is interpretable, I think, but not explainable. I had a lot of questions about importance versus discriminative, but I won't say them. We saw that Spade has been used a lot and also extended, and not only by you, but also by you for the model. Which are not yours. What are the main difference?
Well,
because I don't know, but it's very interesting to see many different.
For instance, if you want to do cross-model search, then for instance, you have a text query and you want to retrieve images. And what this cross-model Spade are trying to do is to represent text, like the text query and the image in the sparse vocabulary space. So it's a bit different in the sense that you need to find this mapping is quite challenging because I know that other people in my team have been working on similar things. And yeah, it was quite difficult. So that's why I also mentioned this general issue of representational basis, because for many things we wanted to try during the PhD, but also we thought about, there is always this difficulty of, okay, if you want to apply Spade in a different domain, in a new language and stuff like that, this question of, okay, what is the vocabulary, how do we initialize it and stuff like that, which is not so obvious. And so far, it's really easy to make Spade work when you really use the vocabulary of the pre-trained language model and you have a MLMA that is well initialized and it's easy. But when you want to change that, it's a bit more challenging. And so it's the same, for instance, in cross-lingual. So you have a query in English and you want to retrieve documents in Spanish. And so you will try to represent things in a multilingual vocabulary, for instance. And here you have also other challenges. So,
thank you. On the slide, 194. Yeah, but I could have chosen another one, but the thing is that the neural models are there is a complete different behavior between the neural models and the lexical one, what I call lexical one, and I understood the best would be not completely as Spade and not completely as BM25 between them.
Yes. So it's okay. it's a bit tricky here because when we wanted to, so when we worked on this, what we would have liked is to actually correlate this with the actual performance. And we thought we would have a good story, but we tried many things, and it's actually quite difficult because here we have like term level measures. First, this measure is not perfect because it assumes, for instance, independence of the terms and things like that. But also, if you want to go back at the query level, then it's not so clear how you can do it. So I don't know what will be. I would tend to say that, yeah, from the point of view of this measure, you want to be as close as 0. But it does not necessarily translate on the actual performance because there are other ways you can explain the performance, for instance, semantic matching and so on. So here we only consider the query terms, and we see that, okay, some models, they tend to retrieve not as much as they should, but there are like other factors that could explain why they are better. And so, for instance, if we look at the performance of different neural models on the MS Marco dataset, it's much higher than BM25, even though they seem to underestimate the importance of this term. So I guess, yeah, it should be closer to 0, but it's hard to translate this to the like effectiveness, like link this to an actual measure of performance. It's quite difficult, I think.
Yeah, so probably another measure.
Yeah.
Better.
Yeah, but something, so I can. We had a paper recently at ECIR, so it's a bit linked, I think, which showed that so when you consider different neural models, and you train these models on different subset of the MS Marco dataset. So we did some clustering of the MS Marco queries, and we trained. So this is not my work. This is the work from Simon from my team, but I helped a bit. And so if you train your model on a subset of MS Marco, and then you evaluate on out of domain from the remaining subset, we see that actually there is a link between the performance and the lexical distance between the clusters. So here we have some like the weighted Jacquard similarity is some measure of similarity between the cluster, and we see overall that if the clusters are lexically close, then the drop in performance is less important. So it's another way to show similar things which are linked to lexicality and.
Okay, thank you. And I have one last question. At the very beginning of your presentation, slide 23.
Do you want me to go back?
We can take 5 minutes.
I mean, you just say something surprising. It was during the explanation of the evolution of the higher domain. And you say that at one time it was more about developing feature, and that developing feature is difficult. But now, at least in NLP, what we saw is that we are just working on developing prompt. So maybe it's the same.
Yes.
So what is your?
Yeah, well, I think it was really from the IR point of view. So I haven't worked on learning to rank methods, but I just know that, like for instance, this type of models in that are used in the industry, they rely on hundreds of features that are like designed by different teams and so on. So we have to think about different ways to think about relevance between a query and a document. So you have like popularity features and things like that. And so I just know that generally you have to design those features, and this might be a costly process. But yeah, I tend to agree with you that now we tend to go back to think about prompts, and so it's a bit similar in a way. But it's also a bit similar in the way that deep learning evolved. Like, okay, we don't design features, but we design new architecture. So yeah, we still have to design new things, I guess.
Okay, so thank you and congrats.
Thanks.
Thank you. I'm giving the floor to Andrew Yates, who is a member of the committee. Can you hear us?
Yes, can you hear me still?
Yes.
Great. So thanks a lot for the presentation and really nice work. I'm impressed with the simplicity and the effectiveness. And I think it demonstrates this can really be a competitive family of models compared to dense retrieval, with several nice properties that dense retrieval doesn't necessarily have. So it's really nice work. I'm very happy you did it. So I have a few questions. I guess let's start with dense retrieval because I mentioned this a bit. So how do these relate, like in terms of expressiveness, in terms of what these types of approaches can model? How does your work with Splayed relate to what we can model with dense retrieval?
Well, I think, I mean, the models are not so different in the end because like you still use the same base pre-trained language model and you have your contextualized representations that you are going to map to different things. But still, I think there are many similarities between the two models. Just that with Splayed, I think that the fact that we represent things in the vocabulary and we try to have some sparsity, making it more like lexical approaches. I mean, yeah, I think it's kind of in between in a way. And what we saw is, for instance, with like dense models, they seem to be less good to do lexical match. So there might be more like prone to drift a bit more, to be more semantic in a way. But yeah, I think there are many similarities between all of those models, even Colbert. I thought about yeah, kind of unifying this at some point in my PhD, but didn't have the time to do that.
Yeah, I think Colbert is interesting specifically because it's also, based in the lexical representations. They're tied to a vocabulary, but the similarity process is slightly different, right? So here with Colbert, we're comparing two different vectors with dot product or cosine similarity. For you, there's a different weight on the query side and on the document side, and so the weight doesn't come from comparing, the term representations. Do you have any sense of if this has any real effect? Are these two ways of getting at the same thing, or is there some difference in like expressive power for search?
You mean between Colbert and dense, or
between Colbert and then say Splayed? So like Splayed Max.
I mean, it's when you think about it, it's a bit different because with Splayed we only have like one weight per term.
Yeah.
And we could like for Colbert, it's more like one vector. So obviously, it's much more expressive. But there are similarities between the two models because so if you look at the Sparta model, I think it kind of bridges the gap between the two, where okay, you take a Colbert model, but you do not contextualize the query embeddings. And so you are kind of doing some sort of like MLM, and so representing things like in a static basis. And I think it really like interestingly maps Colbert and Splayed in a sense. So once again, I think there are similarities, but yeah, of course, Colbert is more expressive, but I think it's a bit more costly too. So.
Yeah, I mean, I think it's interesting. You don't see really strong differences in your experiment. So on MS Marco, Colbert was slightly better. I believe on Beer, the Splayed ++ is slightly better. Yeah, yes. I guess it's unclear where this comes from.
Yeah, but I think once again, we should also always be a bit careful about the results on either on MS Marco or on Beer anyway. I think it's still hard to conclude when we see some improvements if it comes from. We know that MS Marco has a lot of issues. We know there are some issues with Beer too due to like the bias in pooling and stuff. So I agree, but I'm always very careful with the results we have and the way we compare things.
So one thing I find really interesting about this type of retrieval approach is that it ultimately still uses word pieces. So it's never lifted to individual tokens, but you can have like the suffix ing matching, different parts of the document, that sort of thing.
Yes.
Do you have any sense of why this works? Is it because you have short passages? Are these terms effectively ignored? Do you know what's going on here? Or do you have any sense of what might be?
Yeah, it's a good question. So we might think that it's an issue, but what usually happens is that when you have a word that is important, once again, with quotes, usually we split all the pieces of the subwords are predicted in the final representations, which means that basically if it's like in 3 parts, then you will see the 3 parts in the final output. And I think this is what helps discriminating, because you might have a lot of other documents with part of these pieces which initially belong to other words with the same subword. But because you really need to have all the subwords all together, then it's really what helps you like to really discriminate things. But it has some issues also regarding latency and things like that, because when you are in the word piece vocabulary, then you tend to have longer posting lists. And so, yeah, there are other problems. So we know it's a problem, and I think a lot of time during my PhD, we were convinced that we should try to go back to the full vocabulary. We have failed to do so. We have tried a few things in order, like, for instance, to recombine tokens or things like that, which were quite unsuccessful. But I think also one advantage of the word piece, for instance, is that you don't have to care about like pre-processing too much. So, for instance, we see that the model kind of learns to do stemming in some source, because so it's also a good feature in the end. It's not so clear. I think from an efficiency perspective, it's a problem. And I think that some people have been working on that, trying to remap things in the vocabulary. I think I've seen some papers on that. But from like an effectiveness perspective, I'm not so convinced that it's actually necessarily a good idea to go back to the vocabulary.
Have you looked at things like MS Marco document with these experiments, trying to go back to the full vocabulary?
My experiments. Yeah. Sorry?
Sorry, I think there was a bit of lag for a second. I was asking if you had looked at longer documents, like MS Marco document rather than passages, in these experiments that try to go back to the original vocabulary.
No. So we haven't worked on document ranking in the list. I think initially we were not really convinced that there was a good benchmark to do that anyway, because like if you take the MS Marco documents, then I mean, usually it works better if you just like decompose the passages and take the max score. So yeah.
What about the role of like punctuation tokens or unusual tokens in the representation? So when you use like a splayed query encoder, I sometimes see these coming up, sometimes with non-trivial weights, but usually not the highest weight. Are these actually used? Are these ignored?
Yeah, I think it's part of the things I mentioned earlier about strange behavior of the model. Sometimes we either see words that should not be here, but either some weird tokens of the BERT vocabulary. We are not so sure of the reason. Like one explanation we might have is that the model kind of uses those as some sort of latent topics that just add some number of dimensions to your space, and you can, I mean, if the model needs it, it can use those topics to represent things. What will be interesting maybe is to try to check the representation in the end of these topics and see if they are close to some words. I don't know, but yeah, it's true this happens, and I don't have an explanation for it.
If they represent something like topics, does this affect the interpretability of the model? Like, is there a way you can know that the tokens that it actually is using correspond to the original token's meaning in the original language?
Yeah, I think this affects definitely how we can interpret things, but I don't think this happens too often. So this is not like something we see on all the documents like that. Sometimes it happens on documents and we don't really know why, but I think it's rare enough that it's not so much a problem. But yeah, it's true that yeah, I think there will be ways to check whether these tokens actually mean something, like trying to do some clustering, I don't know, and see if they are close to other words. But yeah, once again, still some work to do.
Do you have a sense of if there are failure cases that apply to the models you train more broadly? So not just display plus plus or something, but across variants, are there types of queries, types of documents that are not well suited to these?
You mean when we go out of domain?
Yeah, I guess out of domain is obvious.
Like, okay, I'm not so sure I got your question. Is like, okay, did we observe like failure cases that happened, or?
I mean, any specific trends. So I of course, moving out of domain hurts all sorts of neural IR, but you know, your approach is generalizing better than dense retrieval, for example. But are there any systematic like issues with very out of vocabulary terms? Maybe something ends up as 10 word pieces, or I don't know, anything systemic you see?
I don't think we have seen like a systemic problems. I think it's just sometimes we see, yeah, different problems. I think when I prepared this presentation, I wanted to put a nice example, and then I realized that it was not working. So like I think I had like two queries in the introduction, like using the word concrete. I think they were like, what are concrete terms? And actually, if you look at the spread representation for this query, it outputs things close to the material, which means that it did not really get the context here. So sometimes, yeah, you have failure cases like that. Sometimes we don't really know what is the failure case. Like the bag of words, they seem okay from just looking at the words you predict, but it just maybe like the weights were not well calibrated, which is I think the biggest problem when you go on BERT, like on out of domain, like because for instance, when you go on out of domain, you have new collections and the statistics they change. So there are words that used to be frequent in the data set and now they are rare or things like that, or I mean the other way around. And so with BM25, I mean, you encode this behavior because you recompute your IDF, but with SPLADE, I think like the estimation of these weights are bad. And there should be a way to kind of adapt those. And I think there was actually a paper doing this using some sort of IDF, and I think also using like adding out of domain words when you go on there with SPLADE, and I think it was quite effective.
I'll ask one last question about this topic of learning weights during training. So you talk about like flops regularization and L1 regularization in the thesis. Yes. Why not just take the top highest weights after training?
Yes, it's a good question, and I think it's related to your recent paper. So initially, I think we thought it would make more sense to use a sparse regularization, and I mean it was more elegant this way, and we thought that if we use top K, it should not work as good. It seems that actually using top K is quite effective, but there is also a paper that is coming to next Gaia by my colleagues that they show that actually when you combine both things, so when you first use some regularization and then prune the weights, it's always it's Pareto optimal in a way, rather than just doing top K after training. So there is still something that is learned by the regularization, but it's true that actually just doing top K pruning is an extremely effective baseline.
Okay, well, thanks and congratulations.
Thanks.
Thank you, Andrew. Maybe I'll go with my own questions right now so that you can relax after that, unless the advisors have tough questions to ask after that. It would be surprising. Like my colleagues, I'm going to first to congratulate you for your work, both for your manuscript, for your talk, for your work and your contribution to this field. It's kind of an overcrowded field, so it's not a niche market. It's a big deal to be able to produce important contribution. So when I read your manuscript, obviously my first thoughts were about how your work can apply to my own preferred tasks. So my question will be influenced by that. So maybe the first question would be about the length of the query and the fact that your data set was built for question answering at the beginning. And did you observe a difference in performance between the maybe short queries and long queries, or maybe you didn't look at that?
I didn't explicitly look at that, so I'm not so sure if I can answer. I know that as part of this paper here, my colleague Simon also checked what happens if you train on long queries and evaluate on short queries and the reverse. But I think when you just train the model on MS Marco, there is not like a systematic problem for like longer queries versus short ones.
But why I asked this question is because I was wondering, I don't know exactly how MS Marco has been adapted to IR, so maybe it's not really relevant, but I was wondering how such a system like Slate would be as efficient on question answering tasks with maybe longer questions and shorter answers.
I mean, the thing is that anyway you can control like this kind of the sparsity of your queries. So if you really need to be efficient, then even if your queries are much longer, then this is still something that you can adjust. I don't know how it will perform if if the task is very different, if you have like very long queries, I don't know. But yeah, I mean, I don't see why it would not work.
Okay, and also I wondered for even longer questions for the query, for example, for textual similarity when the query eventually adopted.
Yes.
Do you see any kind of problems that could arise, or maybe loss of efficiency? Or
I think if you have like very long queries, then there will be an efficiency issue because like usually when you really want to be efficient, you want to be queries as short as possible, if possible. So if you have very long queries or even documents, there might be an efficiency issue, but once again, this is something you can also try to control a bit more, either with the regularization, but we know that now like you can either prune the representation after training without hurting too much the performance. Because if you remember the statistics I showed on MS Marco on the passages, you can have like very effective models, which in the end have like 20 or 30 dimensions. So it's not that big. So you can still, even if you're like, you can still like extract meaningful words from the input and expansion words without doing a lot of expansion.
Also about the evaluation metrics, you present the results with the evaluation metrics from the official benchmark.
Yes.
And I think in the manuscript, you very briefly mentioned that this is discussed in the community, but I was wondering if you had the opportunity to really question that and whether your system was influenced, or maybe it could be better or worse than other metrics with other metrics.
So yeah, it's true that there are some discussions about mean-reciprocal rank in IR. The thing is that anyway, we also, for instance, when we evaluate on the track datasets, we use other metrics that are less controversial, and we usually see the same trend. So I think it's kind of at least convenient to use this metric, because anyway, every other paper use it, and so just to compare it makes things easier. But yeah, I mean, we still use other metrics either on MS Marco, like when we look at RICO, but also on track. The thing is that it's really tricky, the MS Marco data set, because we only have like usually one relevant document per query. So that's why we're using this metric, but it's not perfect, and we know that the data set has a lot of problems anyway.
So your goal is to the metrics.
Yeah.
Okay. And my last question is very different. You introduced very well the scientific context, but you did not talk about the industrial context. And it seems to me that doing a PhD thesis at NAVO in IR it's not a detail in the story, and at the very end you mentioned some things about that. Could you tell a bit more?
Yes. So first thing, in NAVO in Grenoble, we are still very much doing research. We are not so close with, let's say, the production services. But sometimes when we have good things that work, then we manage to find some collaboration, and we can try things like at least test things, and maybe eventually put them in production. Regarding Splade, we know that the model has been tested in different scenarios. I'm not so sure it's in production right now, but it has been at least evaluated by different teams for kind of different tasks, but still like retrieval based, which is already good. But I think like transferring technology in any company takes time anyway. So
and so you know that, so you are not involved in
no. So personally, no. Carlos from my team has been working a bit more closely with some teams in NAVO to help them with Splade. But personally, no.
Okay, thank you. Now it's time for the advisors to give a few words. Benjamin?
Yeah, we can start. Also, first want to thank Thibault for all of his work and all the discussion we had during the course of his PhD. I hope we will continue to discuss on IR and other things afterwards. And I guess the other reviewers and the other member of the jury underlined the work that has been conducted. It takes place in a specific context, which is IR, where the competition is fierce. And the space to have new models is very tiny. So it was it was just and we were quite happy to find something that worked, and that worked pretty well actually from the start. So it's usually a good sign when a model starts at the first experiment. It shows that it's quite robust and it works very well. It's not something very tricky to train, so it's a very satisfying model on this perspective. And Thibault has talked a bit about all the work he has conducted under the scene, and which is not presented here nor in the thesis, because I mean there were plenty of trials and plenty of things we tried, plenty of things we discussed, and that were just either crap ideas or we didn't succeed in putting them in the light. But so it's just a part of the work which is visible, but I think it's a very valuable part which is visible. So I congratulate you again on this and all the work. And the only remark I would do is that we were all the time waiting for production like the thesis and things like this. It took a lot of time each time, which is the worst thing, because we, as supervisor, it was quite stressful at some time, and we were discussing with Stefan and say, well, it would be good to have the first chapter next week, and next week was not the first chapter.
Yes,
the first chapter was not there. But the good part of it is that when the first chapter arrived and the remaining chapters arrived, well, the quality was so good that it was very close to the final version, which is really nice, I think, as an output. So congratulations again.
thanks.
Thank you, Stefan.
Yes, so
Do you want to add?
congratulate you again. I remember all your doubts that you had at the beginning of the thesis when things were not clear.
Yes.
And now I think you have really evolved and gained a lot of maturity in your research, because you're able to go in new places without so much confidence whether it's clear or not. So I really saw this transition happening during your thesis, and I'm glad of it. And so I know that you feel this day as like an end, but it's more a beginning for you, for your research career on doing new things as well. So don't forget about this too, and remember when it doesn't work what you experienced during your then at some point there will be some lights. So it has been a pleasure doing this PhD with you and Benjamin, and congratulations.
Thank you. Well, it's time for us to. No, maybe we stay here.
I don't know. Le pont il est ici. Okay, so we move.
We move.
To
Okay.
another
Yeah, but
room.
we have to.
We have to carry Andrew with us. Yes.
No, but we can move. We can move, I think, and we keep the.
I mean, we can use the room in easier.
Okay.
It's the H20, which is booked. So,
Yes.
it's easier if you set up everything here. It's easier that we go.
We have the Zoom
And then we
link.
come
If
back.
we connect to the Zoom link with Zoom, is it going to work?
Yeah.
Your admin, who
I
is
think
admin?
the easiest is that you keep the Zoom here,
Okay.
and we'll set up a new Zoom with Andrew.
Okay.
Andrew, is it okay for you? I will just send a mail with the new Zoom, and we can discuss on that. Andrew?
Yeah, it's okay. I was giving a thumbs up, but it's maybe not visible.
Yes.